we're on number 9. It says use A of t. Now, what A of t represents is acceleration in relationship to time. This is the gravitational acceleration constant. So notice it's negative. It's the force at which gravity pulls something toward the earth. Okay, it's the acceleration rate due to gravity. And we're saying we're going to neglect air resistance. Now, we talked about a long time ago. You would say, well, we would start with something like f of x, and then we can do f prime of x, the first derivative, and then we can do f double prime of x and get the second derivative. Well, when we deal with the equation itself, in a situation like this, the first equation itself would actually be the position equation. And the position equation is S in relationship to T. That's how we express it, S in relationship to T. And then, if we wanted to find velocity, we know that velocity would be the derivative of the position function, right? Because derivative is the slope of the tangent line, which is the blah per blah, or the rate of change. And so that is actually v of t, okay? So when we take the derivative of the position function, we get the velocity function v of t. And we know that if we were to take the derivative of the velocity function, then we could say that we have really s double prime of t, or we could say we have v prime of t, or we could call it a of t, you see, okay? So the position function is the original equation that tells you the distance above the ground that this particular object is going to be at any given time. And the velocity function is the derivative of the position function, which tells you the rate at which this object is traveling upward due to the force of thrust put upon it, or is thrown downward with some force. And then we have acceleration, which is we have gravity pulling down, but we have acceleration, which is the rate at which the rate is changing. It's the rate at which gravity is changing that velocity. Okay, the rate at which gravity is changing the velocity. So velocity is the rate at which the position is changing, and acceleration is the rate at which velocity is changing. Of course, acceleration is going to affect position because it's changing the rate at which velocity is changing position, you see. That sounds a little bit complicated, but that's kind of where we're at. Okay, notice it gave us the second derivative, and so we want to work our way back into the position formula. It actually wants to know how high will the ball go. Now, how high will the ball go? What is that? And I know I hadn't read the whole thing, but how high will the ball go? What is that?
Maximum.
That's maximum. Good. And if we want to find the maximum, we will need to plug something into the position formula, right? If we could find maximum time, or the time at which we have a maximum, then we can plug it into the position function and get our maximum height. Now, it says the ball is thrown vertically upward from a height of 6 feet. From a height of 6 feet. What's that telling us? That's telling us that the initial height is 6. But how can we write that? That would be what? S of 0 is 6. In 0 seconds of time, the position is 6 feet above the ground. That's the beginning of C. So you see how we get that ordered pair? Well, we also have initial velocity. The initial velocity is 60 feet per second. 60 feet per second. Now, remember that V sub t is the velocity formula, initial velocity. And the velocity at time 0 is 60. So at time 0, my velocity is 60, and at time 0, my height is 6. And what they gave us to start with is the acceleration equation, negative 32 feet per second squared, which is the gravitational acceleration constant. Okay? Now remember, we did this at the front of the year. We just kind of developed our formula from a physics standpoint, and here we're developing it from a calculus standpoint, which is kind of neat to see it pull together. So we're going to start out with this. We're going to start out with A of t is equal to negative 32 feet per second squared. We're just going to deal with the numbers here, negative 32. And if we knew A of t, then we could take the integral, right? We could take the integral of, see, the velocity function would be the integral of the derivative function, right? Of the acceleration function. Because acceleration is the derivative of velocity, then velocity would be the integral of acceleration. I'm trying to say all this correctly. So how do we find the integral of negative 32? We assume an x to the 0 power, and then what's the rule? We're going to add 1, and then divide by that same 1. So we would have negative 32 x plus c, right? And let's just call that C1, because we're going to find some more C's in a minute. We'll just call that C1. Now, how can we actually find the value of that constant? What do we need to know to get a value of the constant? Well, we need to know a point, right? We need to know a point. Okay, so we know that d of 0 is 60, right? D of 0 is 60. That means, I should put a t here. Let me put a t instead of an x, because we're dealing with in terms of time, right? Okay. So we know that v of 0 is 60. So that means when time is 0, the velocity function is 60, right? So let's just plug that in. We would have 60 is equal to negative 32 times 0 plus c sub 1. We just plug in that ordered pair, a point. That goes out. And so c sub 1 is equal to 60. So that means my velocity function is really negative 32t plus 60. So we've replaced the constant by taking one of the points that we knew and plugging it in, and the point we knew was the initial velocity, in 0 time, or in 0 second, we're going at 60 feet per second. Okay? Now, to find my position function, I would take the integral of the velocity function, right? I'm going to move this away, and we'll just stop right there with that. So if I were to want to find s of t, the position function, it will be the integral of the velocity function the position function is the integral of the velocity function. dt. I keep putting that x in there. Thank you. The variable of integration. I got to get my variable of integration right. I keep going back to that alphabet. Thank you. And so we're going to have s of t is equal to. So we're going to take that exponent of 1 and add 1, which would give us a 2, and then we're going to divide by that 2, right? So we'd have negative 32 divided by 2 is negative 16 t squared. So we got that. On the 60, there was an understood t of 0, so we would add 1, which would give us a 1, and then we would divide by that 1. So 60 divided by 1 is 60, and then t to the first. And then plus some constant, and we'll just call it C2. So we got that. Now, if we want to try to find C, then we could plug a point in, and the point that we know was that the initial height was 6. So at t equals 0, the function value is 6. So here's my function value. My position would be 6 when time is 0. We can see that all of that would go out, and so C2 would be 6. So my position formula is going to be negative 16 t squared plus 60 t plus 6. Now, let's just analyze that from the standpoint. I'm going to remove my v of t. Let's analyze that from the standpoint of what we did at the first of the year. What is the 6? That is initial position, right? And what is this? It's your velocity, but it's actually your gain in position, right? So it is the initial velocity times time, and that gives you, so we're going to start this off the ground. My velocity is going to thrust it that much higher off the ground, but in front of that we have 1/2 of the gravitational acceleration constant, 1/2 the gravitational acceleration constant. And so we basically derived the idea. We've derived the position formula with calculus going backwards using integration, which is kind of interesting. Okay. All right, let's just go back to this equation to finish the story here. The story was we want to find how high the ball will go. Now we're going to do this with calculus.
Brett
so
Finley to the office.
A maximum. Now, how could we find a maximum? Remember how we found maximums? What is it that might be a maximum? a critical number. A critical point possibly would be a relative max or relative min. Why do you find critical numbers? When the first derivative is 0. Well, what is the first derivative here? It's the velocity function. So I need my velocity function back. What was v of t?
Negative 32t plus 60.
And what I need to do is set that equal to 0. Negative 32t plus 60 equals 0. Because the velocity function is the derivative of the position function. And if I would like to find critical numbers for my position function, hopefully find the relative max or min, then I need to find the derivative, which is velocity. And I need to set that equal to 0 to find my critical number. And so I'm going to subtract 60. Subtract 60. I'm going to have negative 32t is equal to negative 60. I'm going to divide both sides by negative 32. And that's going to reduce to 15 over 8. Thank you. So in 15 over 8 seconds, in a little under 2 seconds, it's going to reach its maximum height. Now, the question is, how high will the ball go? Now, before we go any further, I want to stop and think about this graphically with you. I'm gonna move this top stuff out of here so we can just focus on this. We should know from pre-calculus that if that's a negative, then something is true, and if that's a square, something is true. First of all, if that's a square, what does that mean this thing is? A parabola. And if it's negative, it opens down. So without having to do a lot of stuff and looking for where does it increase, where does it decrease, is it concave up, concave down, we simply know because it's a parabola with a negative a that it's going to be facing down. So this thing is concave down. It's increasing over here. It's decreasing over here. We should be able to visualize that without doing a lot of calculus. And we know that there's going to be a relative maximum there. So we should know there's going to be one critical number, and that critical number is going to be the maximum just from pre-calculus. Okay, so at t is equal to 8, or 15/8, excuse me, we're going to be at that maximum position. Well, where would we plug that 15/8 at? Into the position formula. So we're going to plug that into our position formula, and we can solve. So we're going to have S of t is equal to negative 16 times 15/8 quantity squared plus 60 times 15/8 plus 6, and we get S of 15/8 is 62.25. So the maximum height of that ball is 62.25 feet. Pretty neat use for some calculus. We got to apply integration there. Any questions on number 9? All right. Okay, we're going to move to the next part. That was actually Unit 4.1. All of that was Unit 4.1. And now we're going to get into Unit 4.2, which is summation. when we begin to think about summation, there's some summation formulas that we want to recall, and I'll just try to maybe put them over here. And I'm not going to write the whole thing, but when we have the summation of I, it expands into n times n plus 1 over 2. When we expand I squared, it's going to be n times n plus 1 times 2n plus 1 over 6. When we expand I cubed, it's going to be n squared times 2 plus 1 to the n over 4. Now, we would have all that summation stuff in front of it, okay? So this would go in front of all of those. The sum as I runs from 1 to n. The sum as I runs from 1 to n of I is n times n plus 1 over 2. The sum as I run from 1 to n of I squared is n times n plus 1 times 2n plus 1 over 6, etc. Okay? So that summation thing runs with each one of those. Okay? Now our goal here is to isolate the I or the I squared or the I cube or all of the above. We know that the summation of a constant times our variable is equal to the constant times the summation of just the variable. Excuse me, that's to 20. So we have the sum as I runs from 1 to 20 of 2I is equal to 2 times the sum as I runs from 1 to 20 of I. So we pulled out that constant. Now we know that the I expands into this. And the value of n is 20, okay? Because that's my upper bound, okay? And so what I'm going to have then is n, which is 20, times n, which is 20 plus 1 over 2, okay? So we got that. But we have what? That's just the I part. That's the summation. So when we do this summation, the sum as I runs from 1 to 20 of I, my upper bound n is 20. So in my I formula, I replace the n with 20. I get 20 times 20 plus 1 over 2. But then I've still got this 2, so I have 2 times that result, right? 2 times that result. And you can put that in brackets if you just kind of wanted to separate it, but it's okay. So what are we going to get when we multiply that out? 420? Yes. Just 420.
Right.
Because you got 2 times that over 2 and the 2 cancel out. All right. Any questions on that? See what we did. Are we ready for them to do that? Okay. What we want to do is we want to see I squared I cubed. So we need to expand that. And we'll come over here to the side and do that. The first thing I'm going to do is say, okay, I've got I minus 1 squared, which is I minus 1 times itself, I minus 1, which is going to be I squared minus 2I plus 1, right? And I'm going to have I times that. I just did that part. And so then I have times the I. And so when I distribute it, I'm going to have I cubed minus 2I squared plus I. So when I expand that, I now could write this as the summation as I runs from 1 to 15 of I cubed minus 2I squared plus I. I need to see I squares, and I cubes. See how I got that? Now, on this one, see, we want to separate it because the summation of the sum or difference is the sum or difference in the summations. Okay? And on this one, when I do it, I'm going to pull out that 2. Okay? So I'm going to have the summation as I runs from 1 to 15 of I cubed minus, I'm going to pull the 2 off, the summation as I run from 1 to 15 of I squared plus the summation as I run from 1 to 15 of I. Okay? So we expanded our polynomial into a sum or difference. We got it in terms of I squared, I cubed. On the I squared part, we pulled off the constant. And so now we can expand. Now, remember that my n is my upper bound. My n is 15. When we expand I cubed, it's going to expand into this. The value of n is 15, my upper bound. So I'm going to have 15 squared times 15 plus 1 squared over 4. That's the first part. The second part is an I squared. I'll do that in green. We have an I squared. It's going to expand into this, which we need to memorize. And again, my n is 15. On that one, I have a minus 2 out front, so minus 2 times that I square expansion. And where n is 15, so 15 times 15 plus 1 times 2 times 15 plus 1 over 6 . And then I've got my I, and I expands into the yellow. Again, my upper bound n is 15. So I'm going to have plus 15 times 15 plus 1 over 2. And then we do all those calculations, and we get 12,040. Any questions on number 11? So we created a polynomial in terms of I squared, I cubed. We knew that the summation of the sum or difference is the sum or difference of the summations. We took the constant off of the I squared part. Where it said n, we plugged in our upper bound of 15, and we were able to solve. Any questions on that? Okay. Number 12. The variable does not have to be I, it could be K or any other letter, so we have a letter K in this one, but it's the same idea. What we need to do is get this written as a polynomial so we can see it as sums or differences. So we're going to need to distribute on the top. When we distribute on the top, we would have 6k squared minus 6k. When we distribute that 6k, we would have 6k squared minus 6k. And that should be a k on the bottom, or no, that's okay. It doesn't have to be a k on the bottom because we've got n. K is the lower bound, and n is the upper bound. Okay, k is the lower bound and n is the upper bound. So this is like my I, but it just gave me n cubed on the bottom. That's fine. Okay, so we have, when we distribute that n cubed, then it would pop under each of those, right? Or we could think of this as being 1 over n cubed, and we could pull it off, right? Because we know we can pull that off. Okay? So we probably would be best just to think about, let's just go ahead and pull that off of there, see? Before we do that, you understand that? So we can expand, and when we expand, we're going to have a couple of situations that's got two variables, and then we can pull it off separately. But we're thinking, well, we could just pull it off to start with then, if we can pull it off separately. So let's do that first. Let's go back and just say, okay, we've got right here a constant 6 and n cubed, and let's just pull it off to start with. So we're going to have 6 over n cubed times the summation as k runs from 1 to 10 of k times k minus 1. We just went ahead and pulled off that 6 over n cubed. It would work the same either way, but it's easier to go ahead and pull it off. And then we're going to distribute here, and that would give us 6 over n cubed times the sum as k runs from 1 to 10 of k squared minus k. So we're going to have 6 over n cubed times the sum as k runs from 1 to 10 of k squared minus the sum as k runs from 1 to 10 of k. So now we have it in terms of k squared, which would be like I squared, my variable squared. So now we can do the expansion. And I'm going to close that bracket since I factored that out. That 6 over n cubed is times that whole thing, right? It would distribute in there. Now, the expansion of the square idea was what? Remember that? It was n times n plus 1 over. Okay. Yeah. So it was n times n plus 1 over 2, where n was the upper bound, right? So I'm going to say it in terms of upper bound. It was upper bound times upper bound.
That's a square, it shouldn't be n times n plus 1 times 2 n plus 1 over 6.
Yes. So upper bound n times upper bound n plus 1 times upper bound 2 times n plus 1 over 6, right? I'm going to write it here. I squared was n times n plus 1 times 2n plus 1 over 6, right? So we've done that. My n is my upper bound, and my upper bound is 10. Now, I've still got 6 over n cubed, right? But what's n? So I'm just going to go and rewrite that as 6 over 10 cubed, bracket, right? 6 over 10 cubed, bracket. When I did the summation of the, as k runs from 1 to 10 of k squared, I took my I square expansion. N stands for upper bound. So I have upper bound 10 times upper bound 10 plus 1 times upper bound 2 times 10 plus 1 over 6. And then I have minus the expansion of k, which would be like the expansion of I, which is n times n plus 1 over 2, n being upper bound. And I'm going to put this in parentheses because I would have to distribute the negative, right? So minus upper bound 10 times upper bound 10 plus 1 over 2, right? And then I need to close my bracket. And when you punch all of that in, you get 1.98. Any questions on number 12? Interesting. Any questions on the first 3 summation examples? Okay. So what are we remembering here? We're remembering that we can take the constant. We're going to think about our variable as k runs from. You could say as I runs from or as k runs from. So there's my important variable k. The other stuff we can pull off as a constant. So we pulled off the stuff that wasn't k stuff as a constant outside. We then took the k stuff and we created a polynomial so that it was in terms of k and k squared. And then we said the summation of a sum or difference is the sum or difference in the summations. And we still have our constant out there. And then we said, well, the expansion of k squared is upper bound times upper bound plus 1 times 2 times upper bound plus 1 over 6. And then the expansion of k was upper bound times upper bound plus 1 over 2. And we were able to solve. Okay. All right. Well, number 13. Number 13. Number 13 says use the limit process. Use the limit process. So we're talking about the limit as n approaches infinity. To find the area under the region between the graph of the function and the x-axis over the given interval. Okay. Now, I'm not going to try to draw this perfectly for you, but here's what we're thinking. We're in quadrant 1. This is my x-axis, right? And I've got the graph of 16 minus x squared, and I'm going to be looking at it between 1 and 3. You need to get the visual of this, okay? So 16 minus x squared, the minus x squared means it's a parabola opening down, right? So we don't know what the parabola looks like, not that concerned about it right now, but something like that's going on, let's say, okay? And what we're wanting is the area of the region that's bounded by that parabola and the positive x-axis. So we want the area of that. Okay. And we'll find the area of that next time. Any questions on what we've covered so far? What I want you to be thinking about is how we did that in the past with creating the rectangles, and then think about the limit process as it approaches infinity. And we're going to pull all that together and find the area. And then later, we're going to learn how to marry integration and summation into the fundamental theorem of calculus. Okay? We do things the hard way a lot of times, and then we go, oh, look at this cool little trick. That's what we're doing.